Hey everyone, and welcome to This Explainer. Today, we're stepping right into the shoes of a senior IT engineer handling those incredibly tricky, complex support tickets. We're going to explore the absolute magic of SQL subqueries in a MySQL environment and see how nesting queries can solve these weird Dota mysteries that standard joins just can't touch. Look, we've all been there, right? You're staring down a support ticket, you absolutely know the answer is buried somewhere in the database, but a simple select statement just isn't going to cut it. You know the data is corrupt or mismatched, but isolating the exact rows feels like finding a needle in a digital haystack. Well, today, we're fixing that. We are going to systematically escalate through nested query techniques, adding some serious new tools to your SQL tool belt to solve these exact types of issues. Okay, let's dive into this. Here is our shift at the help desk today. We'll start simple with scalar subqueries, move on to filtering within, and checking existence with exists. Then we'll tackle correlated subqueries, and finally take on a real-world boss fight scenario where a user's access is blocked. All right, Section 1, Scalar, Subqueries, and Select. These are your single value lookups. So a scalar subquery basically does one very specific thing. It returns exactly one row and one column, literally just a single value. And here's our first support ticket. A user is asking to see each order's total cost right next to the overall company average order value so they can compare them. We need a computed column to display an aggregate value alongside individual row data, and we want to do it without writing a messy, complicated join. So here is how we actually build this thing. Step 1. We just write the inner query, which is a simple select average total cost from orders. Step 2, we write our outer query. And step 3, we embed that inner query right into the select list, just wrapping it in parentheses. MySQL evaluates that independent inner query first, it calculates the one single average, and then it stamps that exact value onto every single row returned by the outer query. And this brilliantly illustrates what happens next. Looking at the results, we can clearly see the unique order IDs, their specific costs, and bam, that calculated average cost is sitting right next to them. But remember, this is crucial. If your inner query accidentally returned multiple rows, you would immediately hit MySQL error 1242. It absolutely must be a single value. Moving right along to Section 2, filtering with IN subqueries to handle dynamic lists. Okay, so while a scalar subquery gives us one value, an in subquery returns a single column that contains multiple values. It's basically a dynamic list. Here's ticket 2. Find all transaction records, but only for users who belong to the sales department. The catch? We don't know the exact IDs of the sales team off the top of our heads, and obviously, those IDs change all the time as people get hired or leave. We need a dynamic list to filter our transactions against. Check out this side-by-side translation. It really helps to think about it like this. On one side, our SQL, where user ID in, followed by our subquery. On the other side, just the plain English logic. We're simply asking the database, hey, get the sales team IDs first, hold them in memory as a list, and then go scan the transactions table for matches. It is such an elegant way to cross-reference data. Just to quickly summarize the internal mechanics here, straight from the MySQL documentation, this subquery returns a single column list. But interestingly, under the hood, the database engine often rewrites this IN list as a sequence of equality comparisons and operations. Now, while this is absolutely fantastic for dynamic lists, you kind of need to be cautious. If your subquery returns, say, millions of IDs, using IN can severely bottleneck your performance because the system has to scan and compare against that massive list. Which brings us to Section 3, checking existence with exists, which I like to call the fast filter. So the crucial point is scaling. When we're dealing with massive tables, we have to escalate from IN to a more performant technique. The IN operator gathers up the entire list of values and compares them. The exists operator, however, is a Boolean test. It looks at the subquery and just asks, did I find at least one row? The very second it finds a match, it short circuits and stops scanning. If you're querying a table with 10 million rows, stopping at row 5 instead of scanning the rest is literally a game changer. Actually, I love sharing this surprising little fact straight from the reference manual, because exists only cares about whether a row is returned and not what the data actually is. MySQL completely ignores the select list in an exists subquery. You could write select star, or select 5, or select hello world. It is functionally identical to the optimizer. It's just checking for the presence of a row. That's it. All right, Section 4, let's master correlated subqueries and row-by-row logic. Brace yourselves a bit, because we are definitely taking a jump in complexity here. A correlated subquery is a dynamic subquery that actually references a column from the outer query. And because of this connection, it acts like a repeating loop, executing over and over again for every single row the outer query evaluates. This is incredibly powerful, but yes, it can be computationally heavy. So here's ticket 3, and it's a perfect use case for this. We need to find users who spend more than the average of their specific department, not the whole company. See, unlike ticket 1 where we just wanted the static global average, here the average is a moving target. We need a relative row-by-row comparison. We have to look at an employee, figure out their department, calculate the average for just that department, and then do the comparison. Now, what's really interesting about this is how the math plays out row by row. Notice how the inner query recalculated the average for each specific department. Carol is being compared against the engineering average of 96,750, while Diana is compared against the HR average of 55,000. The correlated subquery dynamically updated its own filter condition based on the department of the current row it was looking at. Pretty cool, right? And finally, section 5, our real-world scenario, the access-blocked boss fight. All right, we've built up our arsenal, and now it's time to put it to the test. We've all seen this classic "system says no" ticket. The user insists they paid, their profile literally says active, yet the application is blocking their access. Something is deeply, profoundly out of sync in our relational tables. Let's pull a quick sample to see what's going on. User 102, they're active and they have a valid transaction ID. Totally fine. But look at user 101. Their status is active, but their transaction ID is null. They are an orphaned row. The application logic is probably crashing because it's looking for a transaction record that inexplicably doesn't exist. Now we need to find every single user in the entire database suffering from this exact anomaly. So let's systematically isolate this corrupted data layer by layer. Step 1, we start our outer query on the users table, just filtering for that active status. Step 2, we layer in a not exists correlated subquery. Step 3, inside that subquery, we check the transactions table for our row where the transactions user ID matches the outer user's ID. Let's move on and see how this all builds together into one elegant solution. On the SQL side, where substatus equals active and not exists, correlating the transaction to the user. In plain English, show me active users who have literally 0 transaction records. By using not exists with a correlated subquery, we just drop any user from our results if the system finds even a single transaction for them. Bam, we are left only with the anomalies. You know, this really brings us to a core philosophy of what we're doing today. To quote the source material directly, subqueries break down a sophisticated, sizable query into distinct logical components executed sequentially. Instead of trying to write some massive, unreadable, monstrous join, we built our boss fight query by thinking logically. Get active users, and then subtract the ones that have transactions. It makes your code maintainable and your troubleshooting process incredibly clear. So as we wrap up this explainer, I want to leave you with this thought. You now have the tools, scalar values, in lists, exists short circuits, and correlated row-by-row logic. What hidden anomalies, what orphaned rows are waiting to be revealed in your systems today? Take these techniques, open up your workbench, and start exploring. Thanks so much for hanging out with me today, and happy querying!